I need to carry that around with me. Where do you want it? Good morning. Firstly, I would like to bring back something from the past, which was 12 years ago. You might recommend, this here is Amin, Kunrad Labuskachny, or Labuschagne, as some of you might know him. That person, I don't know who that is, and that's Karim. That's myself in here. Okay, can I have a little bit of help here? Can we go back to the talk now? Where are we? And yeah, expand it to the whole thing. I open it with the wrong thing. Call L or something. I don't know. There we go. Now we've got the toolbar across there. We need to move that out the way. It's moving the wrong thing. Ah, there we go. That's perfect. Thank you. And okay. Thank you very much for inviting me. And as always, we need to thank the people who fund our work and make it possible for us. That's various of the funding agencies, and this is based on work with Anka Kaluch, Wen Chi, hiding over there, and one of our PhD students who's now an actuary working at a bank, David Rodder. Do I have to do it with? No, it's decided it's not going to talk to it. Ah, there we go. It went to sleep. Thank you. Okay. I'll take you through some of the basics of how we set up stochastic processes in Riesz spaces, for those of you who haven't seen it before. And this is set up in such a way that if you reduce yourself to measures, LP type spaces, things based over measure spaces, you get back classical conditional expectation operators or extensions thereof. Because your classical conditional expectation operators have a problem, and this is a problem that was actually identified many years ago by de Lecherie and Meyer, that you can extend classical conditional expectation operators to maximal domains, and which can be significantly bigger than those from your L1 spaces and LP spaces. And Ben de Pachter also did some work on that with Huysmans and Grobler at some point. Okay, so we take for the purposes of this talk, Dedekind complete Riesz space with a weak order unit. We actually only need Archimedean, but whatever. And I've given you there what a weak order unit is. The weak order unit are things that can be approximated, well, you can approximate from below any element from your positive cone using things from the ideal generated by your weak order unit. So that is there. And for a conditional expectation operator, we require it to be a positive order continuous projection on our Riesz space E and have a Dedekind complete range, which is also a Riesz subspace of E. and it needs to map weak order units to weak order units. So given that, there's always at least one that is invariant under it as well. And lastly, we need the concept of strictly positive. So if you have something from a positive cone and you apply your conditional expectation operator to it, that is 0 if and only if your f from the positive cone is 0. So that's what we mean by strictly positive. Again, this is an apple. It must be apple. Everything goes in reverse. And the next idea is that one can actually extend each such t to a maximal domain. So the first thing is you need to, the natural object to work in is your universal completion of your Riesz space. But in general, you cannot extend your conditional expectation operator to the entire universal completion. And if you just think back on L0, your measurable functions, and you try and extend your integral onto the set of all measurable functions, it doesn't work because your integral is your simplest conditional expectation. It maps you to the constant functions. So that clearly shows you can't always do this extension, but there's a maximal extension. And when we built L1, what did you do? One actually built the maximal extension of the integral over the on the measurable functions. You took some subspace of the measurable functions, usually the bounded measurable functions, ones with compact, you take continuous functions with compact support or something like that, and you can extend that to the maximal domain, and you get L1, in fact. And the continuous functions are not the right things to use for conditional expectation operators. It's very easy to show. If you start out with the continuous functions on the reals, you can define conditional expectation operators which don't preserve those. So the continuous functions and conditional expectation operators are not best friends. That's just to, you've got to get the right mindset. Measurable functions and conditional expectation operators are friends. Continuous functions and conditional expectation operators are not friends. So, okay, so we can do this. We take, to form this maximal extension, we work in the positive cone of our original Riesz space, and we take upwards directed nets. And if that, we require that those converge in EU, the universal completion. And if the operator T applied to that net is order bounded in the universal completion, then we can add it to the maximal domain of T. And then you can extend the definition of T to such objects by just applying it. When we take that increasing net, upwards directed net there, which is order bounded in EU, we can take its order limit, and we call that T hat of F, which was the order limit of the net F alpha, and that gives you an extension to the positive cone, the maximal positive cone, which over here, if I go in the correct direction, which dom T is going to be the positive cone of our new space. And so we form our space by taking E hat, which is dom T. It's difference of two operators from objects from dom T. And we call that space L1T because it works like L1. Okay, so now we've built the extension of our operator. We operate on each positive piece, and we take the difference. How do you form the Lebesgue integral? You do exactly the same thing. You work on the positive cone, and you extend your operator in that way. And as I said, here the essential ideas of this extension can be found in the paper by Hrobler and de Pachter on operators representable as multiplication conditional expectation operators, where they were working in the measure setting. They were not working in the general Riesz space setting in that paper. And just as we've developed an L1 space, we can develop an analog of L infinity. And we now look at everything that was in our L1T space, the maximal domain of the conditional expectation operator, and we require that its absolute Riesz space absolute value is bounded by objects from the range of T. And that is the extended, we're now assuming that we're working in L1T. So that's the range of T on that space there. Okay, and Kunrad, myself, and Wenqi, well, Kunrad and myself looked at some discrete stochastic integrals many years ago in 2010, where we were required to look at an L2 type space. So we introduced that. The L infinity we introduced with one of our grad students, Wenqi, and myself. And Azuzi and Tribalesi have extended this to the general LPs. So they filled in all the, they've done the continuum version. So we did 3 cases and they did an uncountably infinitely many. So, okay, so that's the story of the spaces we're looking at. Okay, so we call a space if, right, wrong button. If we say E is T universally complete, if it is its own L1 space, L1T space. So that's what that means. E is T universally complete if and only if it is L1T itself. Okay, and some of the things you can show then are that the range of T is in fact universally complete as a Riesz space in its own right, and hence as an F algebra. Secondly, then one of the things that comes out of that is if we have a weak order unit that is in the range of T, it's also invertible in RT and hence in E. And all of the LP spaces are RT modules. In other words, you can multiply anything from your LP space by anything from the range of T and end up back in your LP space again. L infinity is an F algebra. Sorry, there's a repeat there. And T is an averaging operator in the sense that if you take an F from the range of T and E from L1T, which is the largest of your spaces, then the product is going to be in E, which is L1T, and T of Fg is F times T of G. And that multiplication makes sense because your F is in the range of T and it is all of these spaces are RT modules. And given that, one can say, well, what about norms? Well, RT is it's a ring. It's not a field, so you can't really talk about norms in the normal sense, but well, you can define something, an object here, which we denote by norm, which takes values in the positive cone of an F algebra F. And we require that it to be, this object here to be homogeneous with respect to the things from the positive cone of F. So that's that condition 2. It is strictly positive and has a triangular inequality, and we will call that, in this case, an F-valued norm, or what we're really interested in, an RT-valued norm, because we have analogs of the LP norms here. The L infinity type norm and the LP type norm, and the one we're going to be, the two that we're going to be interested in for the talk here and that is p equals 1 and p equals 2. We're not going outside of those territories. Infinity, p and 2, 1 and 2. So now, if you're starting to talk about LP spaces, then what comes into play are Holder inequalities. Well, Krobler and Zuzi and Tribulesi both looked at this in slightly different contexts, both looking at stochastic type stuff, but Krobler was looking at Jensen's inequality principally, and Zuzi and Tribulesi were looking at the theory of LP spaces for these type of LP type spaces. Yeah. And they came up with that analog of Jensen, of Holder's inequality. Okay, well, my claim is that we were going to be talking about strong completeness, and for that we need a suitable Cauchy type net, and what we use as our Cauchy net is we say a net F alpha in our space is a strong Cauchy net if this V alpha, which we define to be the supremum over beta and gamma beyond alpha of this RT valued norm, is eventually defined. So we don't need it to be defined for the whole net, but eventually it has to be defined and has order limit 0. Since we're working in Dedekind complete spaces, this is an adequate definition. Otherwise, you have to look at the ordered pair alpha beta and consider that as your indexing of your net. We'll talk about that a bit later. Okay, and we say that the net converges strongly in LP if this object, this vector valued norm, F alpha minus F, is order convergent to 0. And we say that then it is that is the strong limit of F alpha in LP. So it's a type of norm convergence, not really a norm, but whatever, it's very close. And if we can show that, and this is what the talk is about, if we can show that every Cauchy net in LP converges, we say that LPT is strongly complete. And if every sequence in LPT converges, we say it is strongly sequentially complete. Now, we're starting off with the simplest cases and we're working towards the harder cases. One of the easy cases is L infinity is strongly complete. And for this, it's everything works. It's one of the most beautiful spaces. So we take our strong Cauchy net, we form V alpha there. So that's what our setup is. And then we automatically get that bound there because that's the same thing as that norm setting there. And as I said, we're starting with the easy stuff. Sorry, you can't. So we've lost a line there, but we can eventually define the lim sup and the lim inf in L infinity T. We form the difference, and we can bound that nicely using V alpha. And that difference has order limit 0, so we can define our limit, and that is order convergent then. And because this bound here is intrinsically tied in with your L infinity norm, because V alpha came from the range of T, life is easy. So that's where the easiness stops. But note, we only proved sequential. That was this one here. We proved this for an arbitrary Cauchy net. We didn't, there's nothing sequential involved there. Okay, so that's the ideal type of thing that one would hope for. Well, now let's look at the space L1T. Life is not so easy there. And one of the one of the classical Banach space results is if you can show that every absolutely convergent series is convergent, then it's a Banach space. Well, we can certainly prove that here. And it's not hard, as I'll show you. Again, it's an easy result. But that is not enough to show in a vector valued norm that we have completeness. So you have to work a lot harder. Because what did you actually use when you proved that your space was a Banach space? When you used that absolute convergence implies convergence. You used that you could find a subsequence which was exponentially close. So you were using a property of the reals as the range space of your norm. We don't have that. Okay, so that's where so as I said, this is not hard to show. It's a routine exercise. We look at the positive parts of the summands. We form these sums. This is, here we have that this is the partial sums of that are increasing, and we can apply T, and we find that the conditional expectation operator applied to these partial sums is bounded, and hence, using the T universal completeness of L1, each of these sums of positive parts here converges. Okay, and Bob's your auntie, we have convergence of your original series. So we have the convergence of that in L1T, strong convergence. Well, we have order convergence, sorry, order convergence. Okay, but that is where the easy stuff ends. And as I said, in classical Banach spaces, your problem would have been finished at that point, but it's not. And I need to watch my time. When does my talk stop? At 12. Okay. I don't want to spend too long on preliminaries because we have quite a long way to go. Okay, so what we're going to look at here is that, sorry, I have changed between L1 Roman and L1 calligraphic. There's no difference. That was because I took pieces of this talk from different LaTeX files to assemble it. And I didn't quite get around to making everything consistent. Okay, so it got tired of my talk. Time out at half an hour. Okay, so again, we start off now, and I'm only going to talk you through the basic ideas of the talk because of the proof. But what you're going to do is you're going to chop out the original terms in your sequence, and you're going to look at the ones that are exponentially, we've taken that difference there. That's your L1 norm of the difference, L1T norm, and you are looking at when that is below 1/2 to the j times your weak order unit. Okay, so really what you're doing is you're slicing your space into, as we will see eventually, we're going to take the bands generated by these pieces. Those are the band projections generated by that element there. I thought I'd removed all the citations. Sorry. Anyway, and you're going to work on these pieces here, because on each one of these, the bands where that happens, you can work nicely. So you're going to chop your space up like that. We know, because that tends to 0 in order, that these bands when we chop up our space, that adds up to the identity. So we know that we can chop up the space, we can work on each of those bands, we can almost work the way we would in the reals there. And then we combine everything back and we use some of the T universal completeness. And yes, it takes some manipulation. But as you can see here, we've chopped up, we've worked on this band here, and now that enables you to find that everything actually works. That summation makes sense. It converges in L1T, and then you have to start patching things together. And we use the fact that these are disjoint, and we can join them together. We have universal completeness. So as an element in the universal completion, we can make sense of things because they're disjoint. And then you do some hard labor. And the important thing is, because we worked on the different pieces, we have a nice bound on each one. So we combine the pieces and we have that there is uniformly convergent. And now we apply the lemma and we get the convergence we want. And there's the last piece of tying it back to the original elements. Okay, so that's how one does the L1. So, but we only got sequential completeness there. And honestly, I've racked my brains. On the L1T, I cannot get better than sequential completeness. Okay. So let's go on to L2. L2, well, let's look at the L2 space. And our claim is that we can actually get strong completeness in L2. But we have to do it in a diverse and roundabout way. So let's start with some things we can say about L2. Well, we're going to start with maps from our L2 space to the range of T. We say it's T linear if it has homogeneity with elements with respect to elements of the range of T, and is additive and order continuous. We are interested in those properties. So that's what we're going to call a T linear functional. And if RT is a Dedekind complete respace, we have from Ali-Prentice and Birkinshaw that we can look at order boundedness and order continuity in a suitable way. And the next, we're going to denote the space of T linear functionals by T star and call it the T dual of E. But it's not going to be our final object because it's too big. And we can see that this is a subset of the order bounded maps from E to range of T. So we're in the important thing, and that is because RT implies real homogeneity. So, and as RT is Dedekind complete, so is the set of order bounded linear maps. That's from Ali-Prentice and Birkinshaw. Okay, and for each element, so if we take F in E star, the T dual, and if we can find K from the positive cone of the range of T with that bounding there, we say it is T strongly bounded. And we're going to denote the T strongly bounded T linear functionals by E hat. That is where our life is going to work. And we call it the T strong dual of E. On the T strong dual, we have a concept of a norm, just in a very similar way to how you would define it in the real case. And it also has our usual type of bound there. E star has a Riesz-Kantorowicz type theorem that applies to it. Note these are RT homogeneous, and we get the normal, the Riesz-Kantorowicz link between lattice properties and order properties. And the next step in our story is we're going to define this type of Riesz map, which we call phi of f evaluated at g, which is T of fg, for f and g in T2, L2T. And this is a bijection between L2T and its RT homogeneous strong dual E hat. If the map itself, the map phi, is also RT homogeneous and RT valued non-preserving like that. And this is just a little bit about the norm on E hat. We've seen some of that before, and this just tells you that this is actually, the norm is actually a unique minimal element of the bounds. So we can actually, we get everything we want to there. Now, where this ties in with, so that just, let's go back there, one step back. Unfortunately, you can't see it because there's a banner there, but this is the Riesz-Frechet theorem. This is an analog of your Riesz-Frechet theorem from Hilbert space theory. It takes significantly more work than the Riesz-Frechet theorem of Hilbert space theory, I might tell you. Significantly more. And now the next step is this, and this is now where you see the cycle of results. We now have a norm-preserving bijection between our space E hat and our original L2 type space. And the clincher is that we can show that this dual space is in fact strongly complete. And how do we do this? Well, we take our bound there. I don't know how much detail people want to go through. Again, we're going to work via lim sup and lim inf, which are some of my favorite objects. Again, they exist eventually. And it's just, maybe we should go through it. So eventually we have a nice bound here in terms of a V alpha there and the norm of X. Okay, so this is, we're going to build our limits for each X. And we do this in a very similar type of way, but it's a little bit harder work. So we now show that each of the, at X, we can build a limit object, and we define f of X via this common lim sup lim inf value. Okay. And then you just have to tidy it up and show that that's in fact a limit in terms of the norm that we want. Okay. So all of this looks quite nice and easy. And now what do? We use this norm-preserving bijection between the two spaces to get the completeness. Thank you.
Are there
Yes.
You have shown this result for L2, so a natural question, I guess, I mean, you said yourself you couldn't prove things for L1. If I look at your L2 result, where you prove that it's isomorphic to its own dual, and then you prove the completeness of the dual, natural thing to do now would be to take L1, prove its dual is then infinite.
Yeah, well, it'll have to be via a dual argument. What I meant is, I do not know a concrete way of working with L1.
But can you prove duality results?
I haven't tried that. My starting point was, what's the easiest dual to work with? An L2 type dual. So could we get it to work there? And the answer is yes, we can. The first half of this, the Riesz theorem, you can find on Archive. I haven't posted the rest of this talk on Archive yet. So that's, as it is, it's two fairly substantial pieces of work to get to this point for L2. So yes, there's whether you can do L1 via duality. Obviously, using functional calculus and all that, can you do all the other LPs? We've got L infinity. My suspicion is you can certainly, it would be strange if you couldn't do the other LPs for P bigger than 1. So the problem comes down to what, can we get a nice duality representation for the dual of L1 in the Riesz setting? And I haven't looked at that, honestly. Because this was, we only got to the point, Wenchi and Anka, of being ready to talk about this about a week or two ago. That's where things are at. And we've been chiseling away at this for the whole of lockdown, actually. Since the beginning, since I would say, we all met in Dresden in 2019, wasn't it? And started this project then, and this is where we are now, N years later. So, and yes, I mean.
I have a question.
Yes.
So I can't wait. When I see you with this agent of God,
yes,
you can see that as Professor said, wide area by the Russian guys of Platysnovy spaces, a lot of things done in this duality, in this norm. There's a lot of.
I know some of Khosrow's work. I do not know all of it. Okay. I met him in, I think, as far as I remember, I met him in Belfast in 2005 or something like that, yeah. And that's, I was looking at a Radon-Nikodym theorem for conditional expectation operators, and there were a couple of people who came and talked to me about Maharam operators and how some of these things fit together back then. So yes, I am aware of some of his stuff and how some of it relates to what we've done. I do not know all of it by any means. And yes. So I have another, well, I'll leave the other question that I have to Jonathan to tell you about. Because that relates to conditional expectation operators, their representations and tensor products, which I have some ideas, but that has to wait. Yes.